Hello everyone, welcome to Stochastic Calculus for Finance 1, and this is section 6.4, where we'll be talking about the forward measure. So our goals in these sections are twofold. First, we're going to be talking about this forward measure and specifically a motivation. Why should we care at all about what a forward measure is? What is the use of this thing? So that is going to be the first thing that we're going to be talking about. And then second, once we understand or at least give a vague idea about why we should care about this, then we show the risk neutral measure and how can we move from the risk neutral measure to the forward measure. And here by doing that, we'll be able to even see even better the main idea behind why we're doing all this and how it is important. All right. So forward measure, let's try to give a motivation for this. So if you say VM be basically the payoff at time M of some type of contract that depends on interest rates, right? So that means this VM here is a stochastic is a stochastic variable essentially, right? And we know how to price this. There is nothing new here. We know that we can use the risk neutral pricing formula, right? So we have a timeline, we have some type of payoff here, which is then if you want to find the value of the contract, we take the expected payoff and then discount it to the present, right? That's what that's the main idea behind how you can price call and put options within like the Black-Scholes formulas, etc. But then remember, now we're working in the case where interest rates are not constant. So in many cases, you will see that there will be the simple assumption that interest rate is, for example, 3% and is considered fixed inside the model. But we here are allowing interest rate to be stochastic. So that means the discounting factor as well is stochastic. So that's something to keep in mind. So from the risk neutral pricing formula, naturally we can price it this way. So we take the payoff, discount it to the present, and the expected value of this quantity. Nothing new here. So we can say that this, and very loosely, that the computation is relatively hard. And why is it hard? Is because we need to know the joint distribution, and this is the key. To be able to do this, you need to know the joint distribution of DM and VM under the risk neutral measure P tilde, right? And the reason why you need to know the joint distribution is because basically, this is a stochastic random. This is random variable. This is a random variable, and we don't know that they are independent. They are potentially dependent. So there's a lot of things that we need to know. And when just working now with these joint distributions, it can be hard, right? But then luckily, there's some type of trick that we can use, and the trick is to use this thing called this random decoding derivative, right? To change to a different measure. And this random decoding derivative, we have seen that in section 3.1, we have our videos on there. And I think it will be important to watch that just to remember what we're trying to do here. And then ideally, somehow, by doing this change of measure, we're hoping that at the end, we'll get something where the math will be a lot easier than this. And that is the key idea. So let's see how that can be done. So now let's talk about how we can move from the risk neutral measure, P tilde, to this thing that we're calling the forward measure, PM. So we define the M forward measure. So notice like the forward measure is associated to a time period or to a certain time in the future. And here we're working with M. And we define this M forward measure by this expression here. And in between this expression, this Z here is the random decoding variable. And if you remember, we covered this quite in details in about section 3.1, and I have videos on this, where we introduced the random decoding random variable. And we define this random decoding variable Z by, and what we're going to use for this is this expression here, which is just the discounted rate from time M to today, and the zero coupon bond that is maturing at time M. This is what random decoding random variable is. And if you notice here, we can actually have a second expression for this. If you divide both sides by p tilde, right, then you're just getting this essentially. Okay. So now these are very bold statements, right? So we said that this guy here, given by this expression, would be an M4 measure. So we need to verify that, and we can do that by checking that this expression is true, that the probability of all the elements that are in our universe is equal to 1 when we sum them up. All right. And then we need to verify also that what we have here actually meets the standard of a random Nikodym variable, right? This ZW means the standards. And what are the standards? Well, the expected value of Z needs to be 1. At least like the probability that Z is positive is 1. The expected value of Z is 1. And then we also can show that the expected value of a random variable Y under this new measure that we created M, this measure PM, is actually nothing but the expected value of Z times this random variable Y under the Riesz-Natal measure, right? So this will essentially give us a way to move from one measure to the next, from the Riesz-Natal measure to this 4-hour measure. So let's show this. So let's start before verifying that it is that this guy is actually a measure. So what is the probability? What is PM of all the element of omega, right? So that is just like essentially the sum of all its individual element omega inside small omega inside the universe, right? This is all these probabilities that we're taking and summing them up. And naturally, we can actually just replace this guy here by its other expression here, its value, right? That's all we do. And then we know what this we say that we're taking as a random Nikodym variable. We define it as the discount factor divided by the zero coupon bond, right? So simply some replacement here. And the value of the zero coupon bond that mature at time, and we know this price today, right? So there's nothing random about this, so we can actually take it out. And this is a constant among all the summation, so we can just take it out. That's perfectly fine. And if you look then what we were left with, inside we have a discount factor, right? We have a random variable that depends on this output omega, and we have its probability of happening. Well, this is nothing but an expectation, right? This is just the expected value of this guy under this measure. That's nothing that we this is just a very simple correlation. But then if we look closely here, we have seen this before. This is nothing but the Riesz-Natal pricing, right, of an instrument that's paying $1 at time dm. This is just basically the price of a zero coupon bond that's spending $1 at time m. Then naturally these discount each other and we have 1. So we have shown that this is equal to 1, right? Then now let's look how we can show this. So first we want to show that that Z will be positive no matter what. Well, when we take the discounting factor would be actually positive, right? We're discounting from one time future to today. That discounting element is positive. And also the value for zero coupon bond is positive also, right? We're getting a cash flow at time M. So the price today is going to be positive. It's not going to be negative, right? So then this Z is just the ratio of two positive numbers. So naturally this Z is going to be positive. And we know that since this is always going to be positive, then the probability that Z is positive is 1. So that's fairly simple. So now if you want to show, let's try to compute the expected value of this of Z under the Riesz-Natal measure, right? Well, if we look at expected value of Z is nothing but the expected value under the Riesz-Natal measure of this expression here, which is similar to what we did here actually. We're taking B0 1M out because it is not random. And this is nothing but the definition of the zero coupon bond. So so we have shown this one, we have shown this one. Let's show the last one now. So we compute, let's try to compute this. So the expected value under the forward measure M of a random variable y is nothing but all the y elements multiplied by their probabilities, right? Nothing too mysterious here. And then what we can do, we can replace this guy by PM, right? This is just a relationship. There is nothing that we don't know. So we have then that the product of these two random variables multiplied by the probability under the horizontal wall. So if you look closely, then we have some type of something that's random multiplied by some of these probabilities. So this is nothing but the expected value. And what's the expected value? The expected value under the horizontal measure. So we have shown this last element here. So that means that now these two bold statements, we can feel good about them. Now this might seem so esoteric, but so now let's go through what we wanted to do. So remember that all you wanted to do is simplify the computation of this thing here, right? And we want to simplify this by changing the measure to the M4 measure. That's what we want to do. So then this expression here is nothing but exactly what you have down here. So we have the elements multiplied by, weighted by their probabilities, right? And we sum them up over the universe. This is simply the definition of expectation. So nothing too mysterious here. And then what we can note is, like, from this, when we look at this expression here, essentially, we can find that P tilde is nothing but is equal to this, right? So we're just doing some algebra, essentially. This P is coming at the top, right? And then here, the B0 is coming at the top here, and D at the bottom here. So just some simple algebra from this expression, we can move to this to see the value of P tilde omega. So that means what we can do is we can simply replace P tilde omega by its equivalent expression, right? We can absolutely do this. And notice then here what is happening. We have this guy here, which is going to be canceling out, simplifying with this guy, this B0M. If you want, we can take it out, and that's perfectly fine, right? And that's what we have here. So we just simply simplify these guys here. Just some simple simplification here. We take the B0 out, and we're left with this. And if you pay attention, you will see actually we have some random variable multiplied by its probabilities. This is nothing but essentially the expectation under the forward measure, right? So notice what happened actually now. We started by trying to compute the expectation of something that had two random variables inside. So this will require the use of some joint distribution. And suddenly what happened here, now we need to just compute the expectation of a single random variable, right? So which one of these two math will be easier? Well, certainly this one will be a lot easier because we don't have to deal with like this joint distribution, worry about correlation or other dependent. None of that. Here we just have one random variable and that's it. So this is where actually the magic happens. And what happens there, if you look very closely, what happened is essentially here what we did was we were able to eliminate these two terms. And by doing this, we eliminated, we seriously simplified the math that needs to be done, because we essentially removed something that's some two stochastic random variable, and the only new thing that entered was a constant, right? Yeah, this is a very key idea actually, right? We have random variable which can have a very weird or strange, complicated distribution has been dropped from the math, and this makes it a lot easier. This is the main use and the main idea behind this change of measure technique. And every time in financial mathematics, we try to find, okay, which measure can we use which random Nicodim derivative variable can we use, so that somehow along the line we can do this, the math simplifies itself. Okay, so in recap, what we did, we talked about the FOIA measure and why we should care, and then we show how we can actually move from the risk neutral measure to the FOIA measure. And while doing that, we saw the key idea, and we have seen how it can simplify the math, which is a major trick used in financial math. All right, thank you.